Hey everyone, so this is just a quick little 10 to 15 minute lecture on planar reflection. Planar reflection just means that the surface is relatively flat, so it's not a curved surface. Okay, it's a pretty straightforward thing, but there's some cool applications of it, and we'll get to those. There'll be a quick video in the middle, and other than that, everything should go fine. All right, so law of reflection. The basic idea of the law of reflection is that when light reflects from a surface, it reflects back. So if you have light coming in like this, it's going to bounce back like that, right? So all that's telling you is what's called the angle of incidence, the angle of light coming in, is equal to the angle of reflection here. Now notice, those angles are measured for what's called the normal. This dotted line here is the normal. This solid line is like the mirror. Okay. That means that if light's coming straight in like this, perpendicular to the surface, its angle is 0, right? Because that's where we're measuring from. We're measuring from that perpendicular line. This would have a small angle of incidence because it's almost perpendicular, and this would have a big angle of incidence. Okay, all right. So that's the hardest part of this, honestly, of this law, is just remembering what to measure from. You're always measuring from that perpendicular line. Okay. Now, that does lead us to when you have objects that are not smooth or are only like smooth in parts but not totally, you get some weird results. So this is called specular versus diffuse reflection. This is diffuse reflection. Like you see all the light beams are coming in, and we're doing the law of reflection every time they hit. We're measuring the angle of incidence, we're making the angle of reflection the same. But the difference here is that because the angle of incidence, even though all the rays are the same, because the surface is different, the angle of incidence changes. And so the angle of reflection changes. And we get all these weird reflected out things. And that creates an image that's kind of blurry and weird. Okay, this is like when you would reflect off of something you can, I don't know, like the surface of maybe some like not smooth water, or like, you know, like off the surface of some metal, right? You can maybe see a little bit of an image, and the more scuffed up it is, the less clear the image is. But here, where we have like essentially a mirror, the angle of incidence is the same for everything because the surface is flat, and so we get the reflection is the same. The angle of reflection is the same for all of them, and we get these parallel rays coming off, which means we get to see the whole image. Okay. All right, so one of the cool things you can do with this is make what's called a corner reflector. And they actually put one on the moon. And so we're going to watch a quick little Mythbusters video about the corner reflectors we put on the moon and how they prove that astronauts have been there. So let's watch that.
There's time for just one final test. And not just any old test, but the ultimate proof of man's moon mission.
What's this?
A reflector.
In fact, it's called a retroreflector, made up of many tiny prisms just like this. And did you further know that the Apollo astronauts were nice enough when they visited the moon to leave several of these on the surface so that Earth-bound scientists could point lasers at it and gather information about the moon?
So what you're saying is that we get a really big laser and point it at the reflector on the moon, and if we get a signal back, that means that we were in fact there.
Precisely. Okay, it breaks down like this. A retroreflector bounces light back at the light source, regardless of the angle. This differs from a mirror where the angle of incidence has to be perpendicular. So, if there was a retroreflector on the moon, and we knew its exact location, and we had a powerful enough laser, we could detect the reflection and prove there is man-made equipment on the moon.
What are we supposed to be doing?
Technically, we're supposed to have a conversation about where we are.
Oh, you mean like the Apache Point Observatory? This thing right here is the Apache Point Observatory. What a view. And these guys have the tools that we need to put the final nail in the coffin on the moon landing hoax.
Yep, up here in the Sacramento Mountains, New Mexico. Adam and Jamie meet one of the observatory's top docs, Russet McMillan.
How can I help you today?
Well, it seems that there are some people that do not believe that man has actually been to the moon.
I've met some of them.
What do you think?
I think they're crazy.
A bold statement, but Dr. McMillan has the hardware to back it up.
Here's the thing. This little laser pointer is about 10 milliwatts. That's great, but it's not going to make it to the moon and back. That thing, however, peaks at 1 gigawatt. That's 100 billion times more powerful than this is. That's what you got to have to make it to the moon and back.
This is actually not a bad
imitation of exactly what's on the moon that we're shining the laser into. In fact, the specific one we're shining into was left there by the Apollo 15 crew. Now, we're firing on the order of 200 quadrillion photons per laser pulse at that reflector, and we're getting between 1 and 3 photons back per pulse if we're lucky. When we get that photon back, we'll see a spike like that on the screen.
I am slewing the telescope to the lunar highlands.
Slew away.
Test number 1, shining our laser at a portion of the moon's surface devoid of all man-made objects, including retroreflectors, known to locals as the lunar highlands.
There's the moon. You can see the craters.
With the laser pointed at a random location on the moon's surface,
Initiating laser.
Dr. McMillan pulses 200 quadrillion photons into the night sky.
So we're shining the laser on the lunar highlands now, and we're getting nothing back except background light.
As expected, the lunar regolith, with its reflectivity index or albedo of approximately 8%, simply scatters the beam, and the sensors back here at the observatory detect no reflected light.
Now I'm going to move to Apollo 15.
Woohoo! Apollo 15, crewed by Scott, Irwin, and Warden, set down at the base of the lunar Apennine Mountains, which is where they placed the retroreflector.
Wow,
That's the location where Apollo 15 landed on the moon.
that is so cool.
Initiating laser on retroreflector from Apollo 15. And there's a spike beginning to stand out.
Is that it?
That's the return from Apollo 15. Light returning from the laser retroreflector at exactly the wavelength and distance that we were expecting.
That is so cool. I know you do this like 100 times a year, but it's really thrilling to watch it happen right in front of us.
Not just thrilling, but conclusive.
Look, I'd love to go to the moon, but I can't. At least not right now. So we did the next best thing.
We shined that laser at the moon on the second test, and we got a clear spike back. Photons came back to our receptor. Now, the only way that could happen is if there was a piece of man-made equipment up on the moon to reflect them back.
So get over it. There's no conspiracy here.
We've been there. We've done that.
All right. So, corner reflectors are pretty cool. They obviously have to be in 3 dimensions, but we'll only do them in 2 dimensions because it's a little bit complicated to draw it otherwise. So here we have a corner reflection in 2 dimensions. So we have light coming in, and you can see right here the angle of incidence is equal to the angle of reflection. And then it bounces off that first mirror, comes over here, hits this. This the angle of incidence is equal to the angle of reflection, right? And it bounces back. And these 2 lines are parallel. Now that being at that angle, kind of obvious, but we can do the same thing here. This ray comes in, and the angle of incidence here is much, much bigger, and so the angle of reflection is bigger. Then it's the next one, and we have a small angle of incidence and a small angle of reflection, and it reflects, and you can see again these 2 lines are parallel. So it doesn't actually hit at exactly this the same spot. It actually comes back just parallel. But that's actually pretty good because it's not very far apart. It's just right next to it. Okay, we'll do a couple of problems like this during class, but they can get a little tricky. But it's not too bad. All right. So what about the image that the mirrors create? So what if you're looking in a mirror? So we know through experience that the mirror is there. We can all recognize a mirror. We know what's going on there. But in a fun house, when it's curved or when we're distracted, or I guess if you're like a dog, I don't know if you've ever seen the videos of dogs seeing their own reflections and being super confused and thinking that's another dog and barking at it. It's really funny. My favorite things. But they can be confusing. They can make us think there's an object back there. Okay, so why does that happen? All right, so looking at this, we have 2 eyes. Now imagine this is actually 2 eyes, not 1. Okay, so 1 eye here, 1 eye here. So we're seeing again the rays reflect off of the top of this bottle, bounce by the law of reflection, and hit each eye. 1 hitting each eye. Now they're slightly different. They have to bounce off slightly different places. Now our brains interpret light as if it went in a straight line. So we think of it as not having reflected. We think of it as coming back through here. And so where those 2 lines cross, that point is where we see the object to be. So we see the image of it. So it looks like the image is right here. Same thing with the bottom. Again, it bounces back, and we again track it, and we see the bottom of the bottle to be here. So this is where we see the image. With a flat mirror, okay, this distance of the object in front of the mirror is the same as the distance of the image behind the mirror. Okay, those two things have to be the same. All right. Okay, sorry, got distracted. So these two images, and that's a really important thing there. Okay, we can look at the same thing here. We can do some trig with this. So because the image is as far behind as it is in front of the mirror, okay, you can use trig to figure out how far away like each part of the body looks too, not just how far away the image is, but like if I want to figure out how far away this he's looking at his feet, how far away that is, I can do some trig. If I know this distance here and this distance here, I can see how far away his feet are just by making a right triangle with those sizes. Okay. All right, that's about it for planar reflection. We'll do some problems based on this on Monday or Tuesday, depending on which class. Have a good weekend.